Okay, just kind of review something we did early. Now we have a book, we can look at the table and stuff like that and compare. So Laplace transform of f of t is defined by, that's just, you're integrating f of t against e to the negative st. Now we want to look at that geometrically too, to kind of see what's going on, but do that later. Let's just get the integrals down. So e to the kt, Laplace transform e to the kt, you get a simple integral here, okay? And you simplify this to this form. This is all very straightforward, everybody got this, okay? And if you have to write out the u substitution, that's fine. But if you're used to integrating exponentials, you just know that, well, the antiderivative is going to have it's going to be a multiple of this. Well, the derivative of this is negative s plus k, e to the negative s plus kt, right? So you better be divided by negative s plus k, which is the same as k minus s, okay? And then you can just check this and see that, yeah, if I take the derivative of this, I get a negative s plus k. If I then divide by this, that goes away and I get this, okay? So that's very straightforward. And when they do the u substitution or see it and check it, you can check it in any case to make sure it's right. So limit at infinity, as long as negative s plus k is negative, limit at infinity is going to be 0. Now this is kind of important, okay? Because you got to be careful about the domain of this thing. If s plus k isn't 0, then, if s plus k is not less than 0, if it's greater than or equal to 0, well, if it's greater than 0, you're going to have a positive exponent on the exponential, and you're going to take the limit of that as you approach infinity. That's going to blow up really fast, so it's going to be divergent. It's not going to do you any good, okay? Infinity is not a good answer here, okay? And if s plus k was equal to 0, well, you'd just be integrating a constant from 0 to infinity, and you'd still get an infinite result, okay? So basically, s has to be less than k. S has to be greater than k. So negative s plus k is less than 0. And this minus this gives you this. And then you look up the corresponding Laplace transform on the table and you find that, yeah, that's it. Except your book uses a for the constant, which is pretty traditional. I threw k in there because e to the kt is a very common expression. So if it's e to the kt, then it's 1 over s minus k. Then Laplace transform of t squared, a little more involved, and gives us a pattern that allows us to determine the transform for any value of t, not for any exponent. Okay, so write out the expression, just plug in the t squared for your f of t, and the integral is pretty straightforward, but it's going to take a couple of integrations by parts. I just wrote a little note here. The integration by parts formula comes from the product rule, and there it is. Okay? It's something that should be ingrained after a year of calculus. You got to do the integration by parts. U is going to be t squared, du is going to be 2t dt, which is going to have the effect of making the integral of v du. Your du is going to have a 2t, it's going to be a first power of t, you're not going to have a second power of t. Okay? So you're reducing the power of t, and that should be familiar, but it might be a little rusty. Your dv is going to be your e to the negative st dt, and v is going to be the obvious antiderivative of negative 1 over s e to the negative st. And you then do your uv, which is going to be this times this. There it is. It's evaluated between 0 and infinity, and you'll notice that at 0, t squared is 0, making this 0, right? And at infinity, e to the negative st approaches, as t approaches infinity, e to the negative st rapidly approaches 0, so that's going to just go away, okay? It's going to be 0 at both limits, so you're just going to get a 0 out of it. Then you're going to have the 2t dt times your v, giving you 2t and a negative 1 over s, okay? Giving you negative 2t over s times then the t e to the negative st, and that comes out this. Remember, you're subtracting the integral v du, so that negative sign and that negative sign are going to give you a positive, and you're going to get this, okay? And if it was a higher power of t, what would you get? If it was t to the 10th, what would be the difference? Well, the difference is in this. If you're doing t to the 10th, your du is going to be 10 t to the 9th, right? So you would have a 10 here instead, and a t to the 9th here, okay? And then when you do the thing for t to the 9th, your u is going to be t to the 9th, your du is going to be a 9t to the 8th, okay? And then you're going to get an 8t to the 7th and a 7t to the 6th, and so forth, okay? So the process is going to work out. Now here's the rest of it, but you understand integration by parts well enough to get this, okay? Then you could do t to the 3rd just to see how it's going to go, but pretty soon you see the pattern. Okay? If I ask you to do this thing for t squared, t cubed, t to the 4th, up to t to the 10th, after t cubed, you'd say, wait a minute, I don't have to do all those. I see what's going to happen, right? Because you look for patterns, hopefully. Okay? And if you don't look for patterns, you end up doing a lot of work and missing stuff that's going to be very helpful to you. So we can quickly conclude here. There's a pattern. For t to the n. Easy to see if you think about it, that the Laplace transform of t to the n is going to equal n times n minus 1 times n minus 2 down to 1 over s to the n. That may be a little hard to read what I wrote there. Chuck's not working real well there. Okay. Well, that's n factorial over s to the n, which is, of course, formula you're going to see if you look at the book. Okay.